I want to talk a little bit more about soft manifolds. They generalize manifolds which we have looked at for many years, which I call here just hard manifolds. Hard manifolds are graphs such that every unit sphere is a sphere. So here we are more flexible, so unit sphere can also be contractible. And this gives us more flexibility and also more compatibility with arithmetic and more symmetry. There are lots of advantages. We talked about this last time. So here's kind of an overview over the notions. There is a notion of contractibility, contractible graphs. There is a notion of hard manifolds, discrete manifolds, and then we've generalized. In a nutshell, all the properties of hard manifolds go over to soft manifolds. Today I want to do a couple of things. First of all, I want to talk about the definition. So the definition is now frozen, and I debated for some time whether I want to have requiring here that every contractible vertex can be taken away to keep the property of having a soft manifold. This changes a little bit things. I mean, it just makes it, with this definition we get a larger class. Let me just get you one example here. So if you take this graph, so this is the kite graph. So with this definition, which I have here, this is a soft zero manifold. Let's just see why it is a soft zero manifold. Every unit sphere is here contractible. First axiom is satisfied. And there is a vertex which we can take away such that we keep having a soft zero manifold. This is the deformation. So if we take this vertex away and we delete that vertex, so we get the K3, and K3 is a zero manifold because every vertex is contractible. Every vertex is a contractible unit sphere, and we can take away one of them such that we get the graph, which is K2. And why is K2 a zero manifold? Because again, every unit sphere is contractible. The first axiom is satisfied. The second axiom tells you we can take away one of the things, so we get K1. And then by definition, K1. So what happens with K1? Every unit sphere is an empty graph. Empty graph is a -1 sphere. So that's, in this case, this is actually a hard. This is also a hard zero manifold. This is the unit 1 in the Shannon ring. Stronger requirement. So let me just maybe call this axiom A here, and this axiom B. So and then we say B prime is every G minus B is a soft B manifold. So that's different. With this definition B prime, this kite graph is not in the class. The reason is all vertices are contractible, so G goes to, now we have the path graph D3 with 3 vertices. This is not a D manifold for any D. Why? I mean, what happens is every unit sphere here is really contractible or a zero sphere. So it can only be a one manifold because this unit sphere here is the zero-dimensional sphere. So this can only be a one manifold because one of the unit spheres is already zero dimension. And these are contractible. So, but if you take that away, so there must be by axiom B prime or B, doesn't matter, you can take one away. So if you go here and you take one vertex away, it doesn't matter whether you take this contractible away or this contractible away, you end up with K2, which is a zero manifold. So this is a soft zero manifold because every unit sphere is contractible, and if you take one away, you get to the K1, which is a hard zero manifold. The only contractible one, the only connected zero manifold, hard zero manifold, is K1, the one element. And maybe I give you a reason why this definition is preferred over this definition B prime. So there are several reasons for that. The first reason is it's easier to check that something is a soft D manifold with this definition here. You just have to give a sequence of homotopy deformation which gets you to something which you know is a soft D manifold. So requiring that every reduction is soft D manifold requires much more work. And the goal is, of course, to use this in applications. So you have thousands and thousands of points, and most of the points are contractible, and so you don't want to go through all the points and see whether you end up with something which is a D manifold or not. You just want to take one away. All these things were just chosen so that you can prove that we can prove theorems. They are not yet finished. Work in progress. You see this chisel and hammer situation where we work with some definitions, and what eventually will have to work is that you have theorems. And I mentioned the theorems already, and I will mention them today again. So there are three theorems which we want to prove. The first theorem is that we want to show that it's invariant under Shannon multiplication, strong multiplication, which is really the very natural framework for graphs because it's compatible with Euler characteristics, compatible with the cohomology, compatible with curvature, compatible with spectral notion, so everything works. You have tensor products, and for the Laplacians, and all the things all the nice things you want to have happen for the strong product. So you want to have the manifolds when you multiply them stay manifolds, but that's not true for the hard manifolds. And so the reason why we introduce soft manifolds is the product of two hard manifolds is only a soft manifold. So that's one theorem. The second theorem is that we want to be able to show that every of these soft manifolds can be reduced to a hard manifold within the class deformed to a hard manifold, which is also something very natural. You want to actually, what you do when you have data and you get a point cloud, you want to actually get a hard manifold, nice triangulation. And the third reason is that a sufficiently dense set in a Riemannian manifold should be, Riemannian D manifold should be such a soft manifold. Doesn't matter how that point cloud is random, if it's just sufficiently dense, then you have and for that, especially for that, we need this kind of definition B and not the definition B prime. Also, we want to have notions like the edge refinement should be. So here's another reason why I like this definition and not the B prime definition, a soft one manifold. Why is it a soft one sphere? Because I can take this. There's only one contractible vertex. I can take it away and I get the hard one sphere. So if I make an edge refinement, take this contractible, this remains contractible. So this I can take away also with a stronger definition. With the definition B prime, this vertex W cannot be away. With the B prime definition, I must be able to take any vertex away which is contractible. Take W away. I take W away, what actually happens, this is a graph with a spike. This is not a soft manifold, even with that definition here. Why not? I mean, the simple reason is that the unit sphere of this vertex here, it's not a discrete sphere anymore. It has 3 points, and that's another reason why I like this definition here. The wheel graphs, the only chance what you can have, the only way this could be a D manifold if it's a one manifold, because there's a vertex which has unit sphere C5. So in this case, this hat has to be, and then the rest is contractible. So axiom A is okay. But axiom B fails. This edge has disappeared, this vertex, every connection to this vertex has disappeared. So this is a soft zero manifold. So in this case, the axioms A and B work for d equal to 0, but it has changed dimension, right? So this was dimension, this was kind of had a two-dimensional nature at the 0 manifold, because so we can remove a vertex such that it becomes this kite graph, and then we have seen already the kite graph becomes K3, and then becomes K2, becomes K1. This reduction here showed us that this is actually a soft zero manifold, but that doesn't work. So we have also complete graphs Kn, but Kn, this is a zero manifold. That is connection graph, which we have seen last time. This connection graph C4, when you take all the complete subgraphs of C4 as points, and you connect to if one is intersecting with the other. Soft is actually really a good name, because what we can do is we can add, you can also add kind of a, you can make extensions over balls, you can also make extensions over balls, you can also make extensions over simplices. So when I'm looking at this, so I can make arbitrary such extensions, and this is always a soft. This is an example of a soft one sphere. One of the reasons why these soft manifolds are more useful is that we can deform within them. For example, we have the task to get from C4 to C5. Of course, they should be considered homeomorphic. I mean, both are one-dimensional circles, but how do you get from here to here? This cannot be deformed within hard manifolds. Of course, what you would do is make an edge refinement, right? Take this edge and add that other vertex here, but that's not part of that tool which we have here. We like the Morse setup. We like this adding of vertices. Restricting the tools is really very powerful. Morse theory is so powerful because it's so simple, because you restrict the functions from C infinity, you restrict it to Morse functions, which have kind of all the nice properties of analytic functions, but they're not that rigid than analytic functions. So it's a genius setup. The Morse setup is a nice thing. You add handles when you build up something. The Morse theory is kind of a guide. And when you use Morse theory, you can only add things or remove things which are... but in this case, I mean, if you want to do that, then stay with the topology. Stay with the topology. So this is, in Morse, yeah, you would take that away, but then you actually have a unit sphere, which is, if you take that away, you have a unit sphere which is a zero sphere, which is not contractible. So this is not a homotopy deformation, but it's a Morse step, or removal of a handle. So, but within this class of hard manifolds, we cannot deform using these tools. And I'm using just restricting also the tools because we want to prove theorems, and having just very few things to check is much easier than having, you know, a large complicated setup. So simplicity rules, and but because it's not possible within hard manifolds, we have to soften it up, and it actually works very well. So what you can do, I showed that in a previous movie. You add here, and so this is when you add this vertex, you still have a soft one manifold, because you can remove it, you get the soft manifold. And now you take this, which is also a soft one manifold. The reason is because you can remove this contractible vertex as a contractible unit sphere, path graph as a unit sphere. So you can remove that, and then you can remove that to get to a hard one manifold, one sphere. You can remove that vertex here, because when you remove that vertex, then you have a contractible unit sphere. The unit sphere is a path graph with of length 3, path graph P4 of length 3. So you remove that, and then you end up with C5. If you have a triangulation of one two sphere and you have another triangulation of a two sphere, of course they are should be homeomorphic. And I've mused about this kind of a couple of years ago. How do you define that within graph theory nicely? It's better to be able to kind of make local deformations from one manifold to another manifold. And for that we need some tools. So that is something we want to do in general. So that's an example, and we have seen examples like that. So we have that, and you add this is a maximal simplex. You do that. So in this case, this is a maximal simplex. What you can do is you can add and then you can add another one. So this is now a maximal simplex. You can add another one. So it has to be a maximal simplex. So you cannot, over that simplex, you cannot make an extension. That doesn't work, right? Because you have in this case, the unit sphere would be 3. So that's not allowed here. You cannot take this here. Pretty clear, right? Because you would introduce a wheel graph, and which would be a two-dimensional point. But this is what I have here is an example of a one sphere still. It's just to demonstrate here kind of how you work. What you have to do is you have just to show that the extension satisfies these two axioms. So what happens is, first of all, you have to verify that the extension, so g plus x v satisfies A. In order to show that it satisfies axiom A, what you have to verify is that every unit sphere still is either contractible or is a soft minus 1 sphere. So in this case, what happens, for example, for this vertex has a unit sphere. So if this is x, as x is actually just this is a soft zero sphere. So that works. It's a soft zero sphere. But you see what has happened, right? If I added this here, what happens is it was actually making an expansion of the unit sphere, and we can use induction to actually see that every unit sphere also remains either contractible or soft unit sphere. Show this, use induction. And then verify, I mean, a new vertex is definitely contractible by definition, but every vertex which is not attached to it doesn't change. Every vertex which is connected to it, what happens with a unit sphere? The unit sphere has this same extension here. So what happens is, so there are 3 cases for x, for v is okay by definition. So every w in SV is okay by induction. This remains a soft sphere. W is not in SV and not equal to V. It means it's not in the ball of V. For example, this vertex, this is not affected at all. All other points are not affected. So you see how we work with these definitions. What we can do is, because they are recursive definitions, we can also use this recursion or this induction in the proof. We can use induction in the proof to prove things like this. There is a second lemma, which it's not a maximal complete subgraph, but what we have is if you have to take a ball, a unit ball. So a unit ball is now this is the unit ball. If this is x, px is this path graph, and what we can do is we can make an extension over this path graph. So that actually was just done. We use this for the deformation. And what happens then, we can remove this and we make a larger. So there's not only a unit ball, you can also define a ball as a graph such that the boundary is a soft d minus 1 sphere. And so we can actually take, instead of a ball. But what you can do is, for example, you can take this. This is a soft, not unit sphere, soft soft sphere boundary. What you can do is you can build extend with this. So this is your x, and you extend with this. So what you do is you add another point and you connect with every point here. It's like a spider. You build a spider web over every point here. Additionally, of course, that's no more a soft. This is no more a hard sphere, but it remains a soft sphere. And so what happens by definition? This point is fine. That's the first thing. Everything away from that is also fine, and then you have just to verify that every vertex here, which you had, or every old vertex here, keeps the same, keeps the property of having either a contractible unit sphere or a d-1 soft d-1 sphere. So what you have is actually contractibility. In this case, you actually get contractibility. The sphere has kind of been there's a pyramid construction over the sphere which has made it a ball. So all the points here are actually fine. These are the points which you actually kind of want to get rid of. These points you can actually get rid of because they are contractible. So you can get rid of these points. And then when you get rid of these points, what you actually have done is you have replaced that complex part of the thing. You have just replaced with a simpler graph. So that's the kind of one of the tools we can then use to simplify manifolds and make them smaller, and also reduce every soft manifold to a hard manifold. So this needs work. This needs work to be done. So what you have to do is you take such a thing. So you have only a soft sphere. You make this a hard sphere by induction. So you have to show that you can actually do that within the graph using these deformation tools. You can make it a hard, and then you can do that replacement. And then we have a vertex which has a hard unit sphere, and you do that. Then you continue doing that until all the unit spheres are hard unit spheres. When all the unit spheres are hard spheres, when all unit spheres are hard spheres, then you have a hard. So the first theorem is, which we are going to prove then in the paper, hopefully this is all going well, is to show that the Shannon product of the strong product of two manifolds, soft manifolds, the manifolds. This gives us an arithmetic compatibility. This gives us a ring. We have then a ring structure if you also allow these discrete unions. So we have different manifold with different dimensions in different connected components, but it produces a ring, a subring of this Shannon ring. So all arithmetic of graphs, you have all arithmetic of graphs, but then you have a sub ring which is geometric, which are these manifolds. This doesn't work, but this works. So this is nice, and it's very nice because of the homological connection. So you have the Kunit, you have a ring homomorphism to the Poincare polynomial. You have spectral properties of the connection Laplacians. These are tensor products under this product, and so tensor products as eigenvalues multiply. So they can serve as multi-particle states, like a Fock space. But you don't have to build up a Fock space, you just have a ring. You just walk in a ring, which is much simpler. But yeah, we have to show that these two axioms are satisfied. This one, then two. So I mentioned this last time. So what you have to do is you have to clean out every unit sphere and make it. So first of all, what you can do is always, that's from the definitions, you can always reduce the graph so that there is no contractible unit sphere anymore. If you have no contractible unit sphere, every unit sphere is a soft unit sphere. And then when you have a soft unit sphere, you have to show that you can make it a hard unit sphere by kind of deforming the sphere, making the sphere, and that uses induction. You use induction to do that, but then you have to do that in a lower dimensional part within the graph. And the third thing is the kind of relation with topological. So if MD is a Riemannian manifold, you essentially just have to be in the order of magnitude of the smaller than the radius of injectivity. It's different than these nerve theorems which you have. But it's essentially also a nerve kind of theorem. You can think about this as a Dieterich Rips graph then for the manifold. Now, how do you prove this? Just what you do is so you have a manifold. You have a, these are, if this is x, this would be the every vertex, every point in that neighborhood, in that square root of epsilon neighborhood is connected to that point x. But now what happens is, if you look at this x, you can actually remove most of these points inside. You can remove the points within a neighborhood of that point. So once you have that, you can remove every vertex close by, and then what you have is then you have a situation which you can project onto a smaller dimensional Riemannian manifold, and there you can use the induction and see that you have on the smaller dimensional space. You know it has to be then a sphere, a d-1 sphere. So that's the idea, but also this has to be written down. But that's another reason why we actually wanted to have just this definition B and not the definition B prime. Cool. So that's it.